In last lecture, we have discussed about the natural frequency, and we analyzed few problems on that, different kind of problems in which we can apply the Newton's second law and energy method as well. Now we will continue our discussion in terms of natural frequency, but in the last system, wherever we see the system is equipped with only springs, right? Now we are gonna add a new thing in this is damping, right? Damping, as its name suggests, it provides and it helps to vanishing the amplitude slowly as the system moves ahead in its defined process, right? So how much time it will take, it depends upon the amount of damping the system. So we are interested in only two aspects, right? Number one is frequency of damped oscillation, right? So it is just a next form of natural frequency we have discussed earlier. So this is what the first aspect we are interested in. Second one is rate of decay. Rate of decay. It means that if a system is having vibrational motion, and as the time goes ahead, the amplitude of that vibration is slowly going to get decayed, or in technical term, it will say that system's vibration being damped out, right? So these are the two primary tasks in which we are interested in, and we will try to calculate this thing again for different system, right? If we talk about different kind of damping, we have basically four types of damping. Number one is viscous damping. Number two is dry friction damping, right? And Coulomb damping is the another name. Third one is solid or structural damping. Structural damping. And the fourth one is slip or interfacial damping, right? Now this name of these four dampings have gives a little bit idea of what sort of system we are talking about, right? Now the first kind of damping, which is viscous damping, is most important type of damping, where we have smaller velocities in lubricated surface, right? And the machine part which is having very small clearance between them. So this kind of damping, viscous damping, is used in this kind of system. Now viscous damping is the most suitable kind of damping that we regularly use in system. The theoretical aspect of this part is that importance is given because analysis of system in viscous damping is quite easier compared to other three, and in general derivation we get a linear differential equation for this kind of damping, right? Second one is dry friction damping. So this type of damping, as its name suggests, when two parts rub against each other and those parts are dry and lubricated. So this is what the difference from viscous damping. Damping resistance in the second case, which is dry friction damping, is practically constant, right? And it does not depend upon that how fast or slow two parts are sliding over each other, right? Now the third part is, which is solid or structural damping. The type of damping is due to internal friction of molecules, right? So this occurs because of the order how the molecules are arranged in a pattern of material, right? Slip and interfacial damping is kind of energy aspect on microscopic level, right? As we know that energy of vibration is dissipated in microscopic slip which occurs within the material, and it ultimately provides damping in these cases, right? So this is what our theoretical discussion so far, and the important kind of damping in this part is viscous damping, right? Now we will try to analyze our system on the basis of previously when we were discussing in the last module, we are having a mass attached with a spring. Now we are going to add another component which is called a damper, and try to get the equation and what sort of forces are going to put over it. We will discuss it one by one, right? Now this is one system. Okay, now there is one mass m which is being supported with one string, right? Okay, it's clear. This is the string, and this is what the damper, right? This is what the damper, right? So the spring stiffness is K, and the damping resistance and the damping coefficient in general is called C. Like we said that the resistive force provided by the spring is given by kx, where x is the displacement given to this mass m. So kx is the force of a spring's resistance. Similarly, for damping there is one resistive force which depend upon c into velocity, which has been represented by x dot, right? Now, so two forces have been included in this, and if we look over the uh, what we call the differential equation of this kind of system, which has been associated with the damper, is again given by Newton's second law, which is inertial forces. Here we have mass into acceleration plus cx dot, which is the restoring force, and another restoring force is of spring force. This we can get from the energy method as well, right? Now, in order to solve this equation, because solution of this equation would lead to many results, then we will I'll discuss one by one those results, right? Now, so upon solving these differential equation, we will get our solution. I'll directly write the solution here, since right, okay, minus c over 2m plus minus under root c by 2m whole square minus k upon m. So this is what the solution for this thing 1 and 2 part, right? Now we need to, here with the help of this solution, we will define a new term called critical damping, which is very essential to understood in this case, right? Now this radical sign right here in this solution, it vanishes when these two terms are equal to each other. We can say it in this way, right? 2m whole square is equal to k divided by m, right? And again we can write here is, now if such happens, this c becomes cc, which is called critical damping. We will talk about its importance and why we are discussing it a little later. So now our cc divided by 2m will come out as under root k upon m, which is the formula of natural frequency. So here we can get a formula for our critical damping, right? Another dimensionless important term in this series is the damping coefficient. Damping coefficient. Damping coefficient, which is the ratio of C by C, right? Which is damping to critical damping, right? Since it is a dimensionless quantity, it does not have. Now, why we have discussed all this? This damping coefficient, which involves damping as well as critical damping, will decide that system is over damped, critically damped, and under damped, right? These three terms is having their own significance in terms of analyzing these system. Now, we can derive three situations that we will have to remember while we are discussing about vibration. When we say our J is greater than 1, this situation leads to over damping, right? When we say J is equal to 1, this situation goes to critical damping, right? When we say J is less than 1, this situation leads to under damping. Now, what are the practical aspects of these three cases? While we say over damped, under damped, critically damped, it is generally signifies the rate of decay of vibration amplitude. You will see it later on the basis of graphs we have, right? How this particular thing is going to get varied. But for now, we'll have to remember all these three situations based on damping coefficient, right? Now, on this basis, if we understand this solution, which is given by for S1 and S2, as I written previously, it will give in terms of J is minus J plus root J square minus 1 omega n. Similarly, for S2, just a negative sign will come in this positive sign place. The entire expression would remain same, minus 1 omega n, right? We can adjust it by putting this J value in this solution, okay? Now, if we try to get the solution for the differential equation, which is for the damping system, which is given by Cx dot plus Kx is equal to 0, we will get a expression of amplitude of the system as a exponential function, right? The expression is good for numerical problems, but we are not here for discussing the numerical problems. We are trying to get a sense that how it is important in terms of vibrational analysis, right? So you can see if it comes as an exponential term, the rate of decay, suppose it is something in e to the power negative xi plus root this xi square minus 1 omega n, something of this kind, right? If it is of this kind, we can see here that this term, if we try to plot a graph for this thing, right, initially the amplitude is going to get will vanish at a very higher rate. As the time moves ahead, right, the rate of decay will get slow down, and after a very long time, and which is called infinite time, the system will come into rest, right? This axis is for amplitude, right? So this is what the case for overdamped system or overdamping. So this is the case for overdamped system. Now this curve represent, we have to keep it in our mind always, that the rate of decay is exponentially going to get vanish with respect to time, and we will achieve the complete equilibrium after infinite time, right? Since it is a exponential decay. Now, after this, the term critical damping, we can discuss it more, as we are going to increase the damping of the system, right? Now, understand this equation. Xi is involved in this, and Xi is certainly the ratio of C to critical damping coefficient to critical damping. And if we are increasing the damping, more sluggish the response of the system, right? That means it will come down to rest very slowly. Okay. Now, theoretically, as I said, the system will take infinite time, but ultimately it will come to rest in a finite time, in finite time to equilibrium position when it is disturbed from the its original position. So this sort of motion is categorized as a periodic motion. A periodic motion, right? This is what the category we got. Since the displacement curve does not showing a repetitive significance in a certain time after a certain time interval. Okay, now we will move to, I hope this point is quite clear. As I said, that you need to remember that graph only for the situation. Now we can discuss a little bit about critical damping here. Critical damping is a barrier between overdamped system and underdamped system, right? That means after which, if we are exceeding this particular part, we will reach out to the case of overdamping, and if you are below this, we are talking about the underdamping case, right? For this lecture, we will limit our discussion up to critical damping, right? As I explained earlier, critical damping is Xi equal to 1, right? Since it is Xi equal to 1, and if we look out for the solution, it is again having the same exponential manner and not going to get decayed completely. So this infinite kind of thing also associated with the critical damping also, right? So we need to keep in mind this formula of this damping ratio. And another thing we have derived for is Cc is 2m omega n, right? We can modify it for our numerical problem, right? Omega n is k by m. So the formula we can get here is 2 root k m, right? So we can write it as changing the variables left to right. We can change it easily, but it can be managed in this way, right? So now we will talk more about the underdamped system, which is essentially having a kind of periodic decay, and this exponential will always follow, right? Since we cannot get rid of it while we are talking about the solution. So in the next part, we will talk about in detail of this underdamping system for which the Xi is less than 1. So thank you.